It's that time of semester, I see. Hopefully they're sleeping and don't have a cold or something. All right, good. So here we are. I want to continue talking about mutation in programming. Let's start by doing this. Okay, so this is my favorite, simplest, shortest example of a program with mutation, data structure with a box where you can change something. So let's do the following. Let's say I do B1 is a box of 0 and B2 is a box of 0. Okay? How many equality predicates do you know? Which ones? Just do it in the air. Show it to me visually. What's one of them? This one, right? Okay, what's the other one? This one, right? Anyone have an extra pair of hands here? There we go, there we go, there we go. Okay, this one. So, we have two of them. It so happens that they also have names. This thing is called, this one is called, actually, what's this called? Identical. And this one is called? Equal always. Okay, so, is B1 identical to B2? Okay. Is B1 equal always to B2? Okay, let me ask you this. Let me ask you the same question slightly differently. The question is B1 equal to B2? I want to take a vote. We're going to vote. Talk to your neighbors and we're going to vote. Is B1 equal to B2? Go. Talk to your neighbors.
It's because they have an average. At one point, maybe the thing is they can change. We don't know anything about it.
5 and 4 and 3 and 2 and 1 and we're back. How many of you vote for yes? How many of you vote for no? Well, this is Brown. Everyone's right. Well, is there a sense in which the yeses are correct? No's. Is there a sense in which the yeses are correct? And yeses, is there a sense in which the no's are correct? So which one are you, first of all? Are you yes or a no?
I said a yes.
You're a yes, so is there a sense in which the no's are correct?
Yeah, because we can mutate them such that they aren't.
Oh, okay. Any of the no's, is there a sense in which the yeses are correct? Yeah, were you a no?
Yeah.
Is there a sense in which the yeses are correct?
Yeah, because like right now they're.
Yeah, so here's the thing. If I just ask for B1, and if I just ask for B2, they're pretty clearly, they're kind of print equal, right? Is there a sense in which they might not be equal? What can I do to demonstrate that? I could change one of them, right? I could stomp on one of them, we bang on one of them. Okay, so I could bang on B1, right? And I could say the value is now 5 instead, okay? And now if I say B1 and say B2, they're clearly different, right? Okay, so there's this funny way in which they're equal but not equal, in the sense that they're equal now but not equal always. And it's unfortunate because we don't have a way of saying, so if I restore B1, right, so I'll change it back to 0. Sorry. So here's B1 and here's B2, okay? So they clearly are printing equal right now. So it'd be nice if I could say something like equal now B1, B2, right? Because we saw that B1 is obviously not identical to B2, right? That one's obvious because we made two different boxes. It's not equal always to B2. I'm sorry, this is very dramatic, I know. Whoa, that's even weirder. Is it back? Okay, I will. There. Okay. So there's a sense in which they are not identical. They're clearly not equal always. But it'd be nice if I could write something like equal now B1, B2, right? Like they're equal at this moment, but they're not equal at all times, right? This is the predicate that I would like to have return true if it existed. Okay? Of course it exists. Okay. So, what is the obvious question? What is the question that runs through your mind? Maybe you have non-obvious questions. Does anyone have any questions at all? What's your question?
Is there a shorthand?
Is there a shorthand?
Is there equal never?
Get back to that.
Oh, shorthand.
Yeah, okay, so I figured everyone want to know what the shorthand is. Okay, so the shorthand is this. Right? It's all equal. Right? So B1 is equal but kind of twiddly. Okay? Is there an equal never? Okay, here is the question for everybody. Here's the question for everybody. I want you to talk to your neighbors and come back and tell me whether you can actually express an equal never predicate with what you already know, or do I have to, maybe it's built in, right? Maybe if I type equal never, something will happen, we don't know. Or maybe we need to go add something to Pirate, or principle of the way we like to teach programming around here is, can you build it for yourself? Could you build an equal never for yourselves? Go.
Mutate one of them, see if the two things are different, equal always, and they're...
Yeah, so they would have to... Why? Right, because like, okay, no, equal never just says they're not right, because they're equal. Exactly, and they're not
Value.
but they're not. Like, when you go with that, they are just
Always never, now it's not that.
so like, yeah, you said that. How are you checking it? I think you'd have to type it. And that's
Check for every single possible. If you type B,
like something like you go to bank, yeah. So if you check I want to see if you type that and then whether they you never need to know that it's and then you do that. I don't know. Is there another one again? Maybe you take into Can you just type it? Or if they're not.
Okay, so it's the same.
But you'd want to make sure that your function handles it. So if the names aren't equal, you get the last one. That's what I'm saying. Like that's not how it's so stupid.
Okay, in 5, 4, 3, 2, 1, and we're back. So, what do you think? What do you think? Yeah.
For something to be equal never, you'd have to check that like for every possible value of each of them, those sets never intersect. So like they're never equal now, and like going through all the possible values.
Okay, so maybe we ought to go through all possible values and check that none of those values, somehow the sets never intersect. That's a possibility, yeah?
Well, given that if it's numbers, for example, the field you're checking, there's infinitely many numbers you can plug in, you would have to do like a negation check that it's not, you can't find a place where it is equal.
Okay, so we might have to do something along those lines, yeah?
I feel like for one of the variables, you'd have to reference the other variable and then say, okay, if you change B2, then it just has to be something that's not equal to B2 every time it's changed.
Something about changing, yeah, okay, there's something about changing, yeah?
If you could give the reference a type, then you could check whether they're different types. And
So if they're different types, yeah, that becomes pretty easy, right? Because you could just check that they're different types and they could never be equal, yeah?
Or if some part of a type.
But you know, we're all like, you know, hipster Python programmers, right? What types could be from, yeah.
Like if you just imagine the like box or whatever data structure it is as a tree, and then you just chop it off at wherever the mutable variables are, then as long as the two chopped off trees are the same, then they can be equals at some point, but otherwise they are never equal.
Something about chopping off things at mutable parts, okay, yeah. There's another hand up here?
I was going to talk about types.
Types, yeah. So, here's the funny thing, right? What is never? Never is not always. Right? We're running into funny notions of what time means. And to say something is never true, that's not the same as saying, well, it's not true now, and it's not always the same, it's not always not the same, right? We run into these very weird semantic consequences. And I just totally love this question. I've never gotten it before, and I love it. I think I'm going to try to work it into 19 in the future. So here's the real problem. We can't actually write this predicate, right? Because to write this predicate, we would have some way of being omniscient. Certainly we can ask, are these equal always? If they're equal always, then it's definitely the case that equal never would say false. If they're equal now, equal never would say false. But to be equal never, if you are not equal now and you're not equal always, we need some way of looking at the entire program and being able to tell, for all the edits this program might make to these two boxes, right, the values will never coincide. Let me give you a slightly perverse example. Here is, so I've got a box over here, okay? So I've got one box over here and I've got a second box over here. And I need to switch the video, otherwise those of you still in bed won't know what I'm talking about. So, what I want you to imagine is that there's two tapes, okay? And there's the tape that goes from 0, 1, 2, 3, 4, all the way down to infinity over here, okay? And there's another tape that goes from 0, 2, 4, 6, 8, and so on, all the way down to infinity over here, okay? And think of these as streams, okay? And so I've got this box, and this box is basically, actually, let me do better than that. Let me do, that's fine. So I've got this box, and this box is a view on the current value of the tape, right? It's basically telling me what's currently in the tape. So you imagine that you have a stream, and every time there's an update to the stream, I put it into the box, so the box tells me what's currently in there, right? It's like a viewport onto the tape. And now what I'm basically asking is to say equal never, I have to be able to prove that at no point will these two values coincide, right? Because if they ever coincide, then for that one instant they are equal. They're equal now at that one instant, which means they are not equal never. That's a pretty hard ask, right? And that would require knowing the entire structure of the program and being able to decide all sorts of questions about the program. And that's going to turn out to be an interesting question in itself.
Why is it like dependent on the program? Shouldn't it just be like equal never, like in any case? Kind of like equal always.
So here are my two boxes, right? If I want to say, are these two boxes equal, are they two identical? No, they're two different boxes. Are they equal now? Well, at this instant, maybe they're not equal. But to say equal never, I have to know that there can't be a future point in time where they might be equal, right? Let's say, for example, what's happening is this box is going 0, 1, 2, 3, 4, 5 up to 10, okay? And this box is going 10, 9, 8, 7, all the way down to 0. Okay? And so at each instant, each of these boxes updates, right? They get, so are they equal now?
No.
Are they equal now?
No.
Are they equal now?
No.
Is there a moment when they might be equal?
Yes.
When? 5, 5. Right? Well, are you sure? Okay. What if I instead start this program with 1 and I end it at 1? Is it equal now?
No.
Is it equal now?
No.
Is there a point when they coincide?
No.
All I did was tweak one value, right? And suddenly they went from being equal never, not equal never to equal never. So without knowing about what the program does to those boxes, I can't say that they'd be equal never. That's the problem. Never is a statement about all points in time. When you had programs that didn't have state, there was no time. If it was not equal now, it was equal never because there was no other time other than this one infinitely long point in time. The moment I introduce state, it becomes a question, not only does it become an interesting question, it becomes a question that's impossible to answer. That's sort of what state does. Yeah?
Couldn't we try and return like a true, a false, or an indeterminate value?
You could. So you could just say, I can't tell, right? So certainly there's the easy way out, which is the 3-valued return. I showed you that in class, right? That you can have a third value, which is say, I just don't know, right? So it could say, the problem is I don't know how it could say true.
They're not referenced.
Well, I mean, I guess if they're not reference equal, yeah. So there's the trivial cases where it's not reference equal that it could say, you know, it's true because they're two. Oh, actually, no. It depends on even then, right? If I'm talking about the value of them, then it's still possible that they're not reference equal, but they might still be equal. So it's not you really can't do anything non-trivial there. Okay? Okay, good. Thank you. You've just killed 10 minutes of my class. I love that question. That was such a great question. Okay. Any other questions about this? Have we beaten equality to death at this point, considering predicates we don't even have? Yeah, we're good? Okay, great. So now I want to move on to the next topic. Let's do this in multiple stages. So what I would like to do is I would like to be able to write a program that matches the following API, right? The following interface. So for simplicity, I'll just write MC, so I don't have to type long text. So I have something called make counter. And what I want is I want to say, when I say make counter, I get back, the first time I call it, I get back 0. Next time I call it, I get back 1. Next time I call it, I get back 2, and so on. Okay? So this is obviously not a... What is MC not? It's not a function, right? Your high school teacher would be extremely mad if you call this a function because it fails the
Vertical line test.
vertical line test, right? The definition of the vertical line test is this does not happen. Okay, good. Okay, so let's think about how to implement this. In fact, even better, instead of me thinking, why don't you think about it? Go, write me the code. Go.
The box is like top of it. Like, I think you do. And then you just like
Show the box and then update it. Please show us.
no, but inside the function initialize you. But you have to think that so maybe you have to assign
Then it's not getting passed.
you can just or you can just do a mod. Rather than this one, then you can take that.
Well, that's what
You can take it one return that. Or you can just like initialize the box and then you return. Well, then because you have like weird human thing counting. Oh, right. Not so you
Are you done writing code? Okay. I don't see any code anywhere. Okay. All right. Okay. In 5, 4, 3, 2, 1. We're back. All right. Give me the code.
Okay, so you have a box of 0,
Okay.
and then you have a block, and in the block you get like a current value, which is the bang, B, yep, and then you
Update the box.
Yep, update the box with
Correlate plus 1.
yep, and then
Return true.
Okay.
Yep.
All right. Ready? Just run it and make sure it works. Okay. Everyone okay with this? Think it's gonna work? No.
Well, no, I think it will, but is there a better?
Well, hold on. Let's just make sure this works. First things first. Okay. Yeah.
Oh no, yeah.
It's a 0 versus 1 thing? Yeah. Okay, good. So, why did that not work? What?
Parentheses at the end,
Make
make
counter.
counter.
Wait, this is what my
No, that should be fine. I'm not sure why that happened. Sorry, I'm not going to worry about that. But something doesn't sound right. Seem right there.
Yeah, it's gonna be like
It's a B equals box 0 in the middle.
I think it was because
Oh,
when
yeah. Oh, yes, of course. Thank you. Yeah, I don't even want to explain that. Okay, good. Yes, that's right. That's why. Yeah.
If make counter isn't a function, why can we use fun?
Because the language just lets you use fun for things that aren't functions. It's like, yeah, you're grown-ups now, so, you can do whatever you want. Okay, there's a slight syntactic annoyance here, right, of having this block and everything be nested one level deep and having to write an extra n. So I've taken up 2 more lines on the screen, and I've lost a level of indentation. So it turns out in Pirate, you can actually put the block right here. Okay? And if you do that, that's equivalent. So it's saying everything that follows is a block. So the point is you have to always be explicit that you want a block, right? It's never going to implicitly give you blocks. But as a convenience, you can put the block before the preceding colon, and it'll let you do it. There's some rules about when you can do it, when you can't. You'll figure it out, okay? So, but you can put the block before the preceding colon, and then that's the equivalent of having written block and end. But you don't lose 2 lines, and you don't lose that level of indentation. Yeah?
Do you even need the block if you just do bvang b plus 1? Because it returns the value no matter.
You know what? There may be another way of writing it. Okay, so yeah, that's a possibility. Exactly what it returns is a little bit of a question, right? Because you want the value, you don't want the box returned, and so okay, yeah. So okay, all right. But anyway, if you can write this, I'm happy, right? The correct. I want you to get this right, and then you can think about how to write it more concisely. Okay, so far so good. Okay, now what I would really like is I'd like a second counter. Right? I'd like another counter. How do I make another counter? What if I want a second counter? Yeah.
Instead of having this whole block, you just return a new anonymous function.
Yeah, so here's what I would like, right? So what I would like is I'd like to be able to make counters. Right? So make counter doesn't actually make counters, it makes one counter for all time. So what I would really like to be able to say something like this. I want to say something like C1 is called this make counter function. So I just want to abbreviate it to MC, right? So that's just an alias over there. So I want to say C1 is that. And now I want to be able to say C1, 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 right? And so I could also say C2 is a make counter. And then C2 is 0, C2 is 1. Right? Then I can make as many counters as I want. That makes sense? Okay, so now just from looking over here, just from this, we can tell that the type signature is going to be a little more complicated, right? Because I need a thing that's going to return a function that I can then call that does the updating, right? So essentially what I want to do is I want to say this, right? That's effectively what I want to say. Okay. So I make a counter. What does that do? It makes a lambda that gives me back this block. And every time I call this, all this works. Okay. So first what I'm going to do is I'm going to make sure everything we had before still works. Right? Okay? Ready? Good. Right? And just to be sure, okay, ready? How many of you think it's going to work? How many of you think it's not going to work? Okay, what am I going to get?
1, 2, 3, 4.
And why?
There's only one box.
So when I hit enter, it is going to fail 3 test passes. Well, that's 3/5, right? Pretty close. That's over 50% actually. Pretty good if you ask me. So the problem is these don't press because the left side was 3, right side was 0, left side is 4, right side is 1. Okay? What is the problem? What is the problem? What went wrong? Yeah.
Well, the box was outside to make counter functions, so like it's.
Well, what's the problem? You're on the right track. You're on the right track. Try to reformulate that. Try to reformulate that. What's the problem?
Oh, do you want me to?
Yeah.
Oh wait, well it's that like, it's calling the same value, like both functions are calling the same value.
Yeah. Let's push that further. Let's push that further. Try to reformulate. Try to reformulate. More concisely. More concisely. Essence of the problem. Essence of the problem. Essence of the problem. What's the essence of the problem? Essence of the problem. What's the essence of the problem?
There's only one box.
There's only one box. Perfect. There's only one box. If there's only one box, everything is banging on the same box. Right? So how on earth are you going to get multiple counters out of that? What we need is, how many boxes? 2 boxes? 3 boxes? 5 boxes, that'll take care. Everyone's needs, this is like Watson, right? Since we're the CIT, Thomas J. Watson building, it's appropriate. Didn't Watson say the world doesn't need more than 5 computers? So like 1 box per computer and we're done. Pretty much. Okay, so what we need obviously in this program is how many boxes? For this set of test cases, how many boxes? But this program right here. This program needs 2, okay? So, what we need to do is we need to make a fresh box to go with each counter, okay? Now, I'm going to do something, but as usual in this course, don't assume that just because I wrote something on the board it is correct, okay? So what I did was I moved that box creation inside the outer lambda. Okay? There's multiple things. This is syntax, it's not semantics. It doesn't tell us what it's actually going to do. It just gives us a piece of code. We can't be sure what the semantics of this is. One possibility is that B equals box actually gets lifted outside the lambda and everything's sharing the same box, right? Another possibility is that B equals box is actually sort of copied each time you do make counter, and so you get a new box on each call of make counter. Another possibility is that B equals box is copied every time the lambda runs, so you actually get a box per run, right? So it's possible that even though I wrote this, the behavior is equivalent to this, right? It's also possible that the behavior is equivalent to this. Now you're thinking, who on earth would do this, right? Why on earth would any language take something that I wrote over here and move it up to line 5 instead? That would be sheer insanity, right? Right, that's actually what JavaScript and Python actually do. There's a whole assignment about that, like the third assignment of CS 173 explores exactly that question, okay? So I'm not going to go into JavaScript and Python over here because this isn't a PL course. So the point is, there are languages that will actually do that, so you can't be don't get too cocky over here, okay? So let's explore each of these. We know what happens if the B equals box is on line 5, right? We know what that means, okay. So that means there's only one box in the world. Before we explore line 8, what happens if that actually runs? The question is, when does it run, right? What happens if it actually runs on line 10? What is the outcome if this runs on line 10? Talk to your neighbor for a moment and tell me what the outcome is going to be.
Say B equals block 0, current value is 0, and then you update it to 1.
Okay, what happens if it's online? What happens if it's there? What happens if it's there? You get? All zeros? I press run and watch it? Yes? Okay. 2 tests passed, 40%. Why did 2 tests pass? Because that's 2 zeros. Okay? Okay? Good. So it's always 0. Can I mess with your brains a little bit? Okay. All of you, I mean, everyone predicted this, right? I mean, you may not have realized, you may have thought 0 tests passed. Admit it, some of you thought 0 tests passed. You forgot that 2 of the tests said 0, right? But the point is, you knew that it always returns 0, right? So because you knew it always returns 0, you knew that it's not actually doing the right thing, and the fact that 2 tests pass is just a coincidence, right? Everyone, right? Yes? Everyone? Anyone want to honestly admit that that's not what they thought? That is what you thought, right? It's obviously what you thought. That's, in some sense, the only correct thing to think. You were making an implicit assumption about how Pirate works. That when you wrote it on line 10, it didn't automatically get lifted up to line 5. It never even occurred to you that it might actually do that, did it? And as I was trying to point out, there are languages that actually do that. So you can write it in one place and actually gets lifted to a different place and therefore changes the meaning of your program. So be careful, is what I'm trying to say, right? Actually understand your language scoping rules. Don't assume that just because you wrote something in a particular place in the program, it actually runs at exactly that point in the program, okay? If you want, I'd be happy to show you some of Python's weird scoping and JavaScript's weird scoping. It's quite entertaining. It'll mess with your brains a little bit. Okay, so that's not what's happening in Pirate. So now the third possibility is that if we put it at line 8, it might. So let's make sure we understand what the point of this exercise was. If line 8 gets lifted up to line 5, what happens to our test suite? 3 out of 5. If line 8 gets shifted down to line 10, what happens to our test suite? 2 of 5. If line 8 doesn't go anywhere, right, it's not like a continental plate shifting around randomly, right? Then what do we get? How many of our tests pass? 0 out of 5 or 5 out of 5? How many vote for 0 out of 5? How many of you vote for 5 out of 5? Why would you think 0 out of 5 pass? Yeah?
I'm not sure the box would exist once the function actually ends.
Ah, excellent. So here's the problem with the here's where the 0 out of 5 comes from. I make a box. Pay attention. I make a box. I run the lambda. This lambda finishes. This call to make counter has finished. So the box ought to just vanish. Everything's done. The box ought to vanish completely. So presumably the next time I call the lambda, maybe it makes a new box. So even though it didn't move line 8 to line 10, it behaves as if line 8 is line 10, which means you won't get 0 out of 0 test passing. You'd still get the 2 test passing. But it's worse. You might get 1 test passing. Why 1 test passing? Because it works the first time, and then the next time you call the lambda, it gives an error. Right? It says I'm sorry, what B? That's a possibility. Right? Okay. Should we try it? Have I completely messed with your brains yet? Yeah, okay, good, thank you. My job is done. Works fine.
I feel it's because that lambda still exists.
Now, okay, great question. We're going to get that in a moment. Now, what I just described sounded bizarre, right? The idea that it somehow forgets about the existence of B, right? that the function make counter finish, therefore B kind of got forgotten would be like bizarro. That's what the C programming language does. Okay? So there is a language where that is the model, where things are by stacks and et cetera, et cetera. Yeah?
Do Python and JavaScript move it up to avoid that happening?
No. You really don't. This is like awesome trolling, but you've already used up 10 minutes of my class, and now you're trying to use up a whole hour of my class. I recognize this phenomenon. I probably shouldn't say this on a record video, but anyway. So, let me just say I recognize the phenomenon. Okay, so. Okay, so, what's going on? Which is like a really bad magic show. It's like a magic show nobody's paid for. Okay, a magic show. So, what's going on here? Again, for our friends who are comfortably sleeping at home. You've actually seen this phenomenon before. You have seen this phenomenon before. In fact, there are programs you have written earlier this semester that if this were not the case, the program would not have worked at all. You've actually been relying on this behavior all through the semester. It's so natural, so obvious, that you don't even think of it as an explicit dependency in your programming life. Okay. Think about, remember I defined a function and in here I did f of x plus delta x minus f of x. That f was outside the lambda. If it had forgotten about everything outside the lambda, when I came back, so let me remind you of the code here. Okay? So what I wrote was I don't care about mathematical truth here, so I'm going to forget about the denominator to save some space. So I said d dx of square is equal to d dx. I used a hyphen, right? So it's ugly syntax. So and I wrote basically lambda x squared, right? And then I said d dx of cube is equal to d dx of lambda x cubed, right? And I could go back and say d dx of square applied to 10, d dx of cube applied to, I don't know, 10, right? None of these interfered with each other. The fact that I had later defined d dx of cube, I'd called d dx on this function, did not interfere with the previous definition in any way. Because otherwise, when I called d dx of square of 10, I should have gotten, whatever, 10 times 100 times 3, 300 or something like that, right? But instead I got 10 times 2 is 20, right? That only worked because each of these calls remembered the corresponding f. It neither forgot the corresponding f, nor did it override the corresponding f. When you wrote your stream functions, you wrote even more higher order lambdas than this. In the stream case, if it didn't remember everything from the point of definition, you would have gotten so many wrong answers it wouldn't be funny. It would be completely screwed up. Okay? All of this only worked because at the point of saying lambda, what a true good lambda implementation does, like this was the great idea in the Scheme programming language. It's like Scheme said, we're going to get this right, and got it right, and from then on there was no reason to get it wrong, even though people chose to. But what Scheme pointed out is when you construct a lambda, you have to remember all of the names that are currently bound and the values that they are bound to. And that thing, that data structure that consists of both the code and all of the name bindings is called a closure. A closure is this richer object that's not just the code of the lambda, but also all the names that are active at that point of binding. And when you call a thing that's bound to a closure, it actually restores all of those names back to their previous state. The mechanics of this is something we cover in CS 173. Okay? So I'm not going to go into the mechanics over here, but the point is because a language with a proper lambda construct remembers those names and restores them correctly, what really happens on line 9 is when I get to line 9, what is the environment? It's remembering that B is bound to some box. Environment is the set of names that are currently bound. B is bound to some box. It remembers that name and remembers which box it is currently bound to. So here, what it's returning is a data structure that has two parts. The first part is this chunk of code. The second part is a memory that B is bound to some box. Okay? That's the value that is returned that MC refers to. Okay? The next time I call make counter, it gets a lambda. What happened? I came here, I created a box, and then I went to lambda and I said, okay, I have to make a pair of things, one of which is bound to the code, the other of which is bound to the name B, bound to a different box. I made a new box. Okay? And so there's actually two boxes sitting in memory. And they're distinct boxes. They both are bound to the name B, but they're bound to the name B inside two different data structures. And so when you go through one data structure and say B, you get this box. When you go through the other data structure in B, say B, you get the other box, and those two boxes are not at all identical. They're different B boxes. And so each time you come through here, this B is referring to a different box. Okay? And that's what closures are. They're that data structure that give you that memory. Okay? All of this is done for you automatically for free by the programming language. You don't see it happening, you don't need to know that it's happening, but it is actually happening. Okay? Questions?
Is this why in iterative languages, iteration is preferred over recursion?
Say that again?
Why iteration is preferred over recursion when you're like doing like graph theory stuff, like because then it doesn't have to save all the states and stuff.
No. It's a long discussion. That's the subject of another homework in 173, actually. So no. I would say it's preferred more for it's preferred for two reasons. One is historical. The other is many languages don't know how to properly implement recursion. And if you don't implement it, then it becomes less efficient. But if you know how to implement it, it doesn't cost anything different. And if you don't know that, then you don't know that. So yeah.
When it remembers the environment, will it only remember stuff that it uses inside the lambda, or
Interesting question. Very interesting question. So that is a standard optimization that compilers make. So the environment itself contains all of the names. But as you're noting, there's no need to remember names that are not being used. And that there's a standard optimization that functional programming language in particular compilers do that say only remember the names that are needed so you don't store other names. It's actually even more complicated than that. They will, more sophisticated compilers will actually reconstruct the environment. Like halfway through you might have stopped using some variables, at which point they'll shrink the environment at that point. Yeah?
So something that I'm a little bit confused about, if you would, like C1, C1 is just like MC with the two parentheses, so like calling a function.
Yeah.
So if you could think of like substitution, like it's just MC.
Substitution is complicated now.
So if you wrote out like MC and then parentheses,
Yeah.
would that be 0?
No,
And if you did it
no,
again-
you could just I could replace MC with make counter just fine.
Yeah.
Okay. The reason I used I made this name is because I wanted to do something else in class today, which I didn't get to. So it would have been helpful for me to have two names, but I can do this just as well. Okay? And
But now if you call it, like if instead of going through C1, if you called like make counter, open parenthesis, close parenthesis, open parenthesis, close parenthesis, which is essentially the same thing as C1, would that just make a new one?
So what you're saying is if I do this, let me add some lines here. Okay, if I do that, what should that produce? I just made a new box, right?
0.
Okay, let's run that. Because each time I'm making a new box, I have to remember the box that was returned so that I can reuse that box once it has been constructed. Each time here, I'm just making a fresh box and throwing it away. I use it once and then I throw it away. I never refer to it again. I make a new box, I use it once, I throw it away. I never refer to it again. Okay, great.
Does this whole discussion only apply to lambdas, or if we had a nested function, would it be the same?
Yeah, so nested functions would work exactly the same way. The anonymity of the lambda is not relevant here.
And then
Yeah.
in that case, can't we think of it as make counter being?
In fact, if you want to, if you don't entirely believe me, we can even do this, right? We could say fun internal. Okay, I don't have a good name for it, so I'll just write internal, and then I have a block over here, but I have to return that function internal, right? Okay, and if I do that, everything's exactly the same.
In that case, can't you think of make counter as its own little world? So if you think of make counter as the whole program, then we essentially have what we had before with the box outside and then a function.
Where is
Make counter is not the whole program. Let me see what you're trying to get at. What are you trying to get at?
Basically, it's before we had box on the outside, then a function that refers to box. And
Yeah,
the box was on the
yeah,
outside.
yeah.
So we think of make counter as
Yeah. So essentially what's happening is previously we had a box on the outside and make counter without the internal lambda, and that was my whole program. What I've done is I've just shifted everything one level of indentation, right? So this has become my whole program, but because the outside is not the top of my file, but make counter, that whole universe is sitting in here and behaves exactly as before, but I can now observe something about that universe I couldn't observe before because I can programmatically write code that refers to each of these files. Yeah, that's exactly what has happened. Internal is now what make counter used to be. Exactly. There's a hand up over here somewhere. Thought I saw a hand up. No? No. Other hands? Other hands? Any other questions? Any questions? Okay. Okay, this is great. This is a good place at which to stop. The key thing to understand is lambdas basically do the obvious natural thing that you were expecting without realizing it and have been depending upon all semester without realizing it. Okay? Just so you know, there's a speaker in the next hour as soon as he gets here. I don't see him here yet. Named Manuel Serrano. And he's been building really cool language.